My name is Elizabeth Gregory. I'm chairing this session. Thank you, everybody, for coming. It's good to have a big room. We have about an hour and a half for 4 talks, so it's going to be like 20 minutes and change for everybody. Our first speaker is Justin Krometis.
Yes.
And he is a Virginia Tech person all the way through. He has a BS in math and physics. A BS in physics, a BS in math, a master's, and a Ph.D. in math. He has experience in academia and the public and private sectors, and he's now involved in national security. And he is here on behalf of the Virginia Tech National Security Institute. All righty, thank you very much.
Thank you. Okay, so my background, my math stuff is mostly on like Bayesian methods for parameter estimation. So I am not a machine learning person by trade. So I'm going to be I collected some lessons learned from my first year in working in AI/ML because I felt like there were a lot of subtleties in it that maybe are easy to overlook. So yeah, so I'm going to kind of walk you through a couple of case studies for that. So really what I'm going to be talking about fall into the class of data-driven models. So there's not, so really maybe just sort of in general, given a series of inputs, X, and outputs, Y, together they make up the data. We're going to be looking for a model that approximately maps X to Y. And so often that model will be a neural network that will be fitting, okay? And the main thing, so, that can fall, as Kyle and I were talking about earlier, that can fall everything from regression here in this third to ChatGPT, to Alexa, to, self-driving vehicles, right? These are all data-driven models. And I just kind of want to contrast those to models based in physics. Okay, so like when you have something in physics, there's like theory that's sort of basing what's going on. And so you kind of have something to check against to see if your model is kind of doing what you expect it to do. So as AI/ML has grown, there are these really great packages that have sort of been developed and that are publicly available, right? So I've listed some over here on the right, PyTorch and TensorFlow are two of the big ones in machine learning, deep learning. RLlib is a big one in reinforcement learning, which is what they use to, teach machines to play games or drive cars and that type of thing. And what's awesome about these is they're free. The algorithms are already implemented. So when somebody makes writes a paper that introduces some new powerful algorithm, they're implemented in these packages and typically debugged. They're very computationally efficient, right? You can run them on your laptop for smaller problems, maybe. You can run them on GPUs, do high performance stuff. There's a huge user base, so there's great documentation, both official and like if you just go to Stack Overflow, right? You can figure out how to use them without too much difficulty. So data-driven modeling has never been easier, right? We have all this power really at our fingertips for free, okay? However, there are some issues with that. Lots of people here are interested in test. So, one thing that, one issue is sort of like, well, how do we check this thing, right? How do we make sure that it's doing sensible stuff, right? We don't have any theory for the most part to guide the results that we're being given by these models. And they're really like mostly black box, right? So there's not, you may not have a ton of intuition about what's going on internally or sort of what's driving decisions. In particular, like we don't have a lot of guidance about how you choose hyperparameters. And by which I mean like in a neural network, the layer size, the number of layers, the activation function you pick. Often what we're doing is like trying to train a lot of models and then just sort of seeing which one does the best, okay? So this is all just to say, it may not be clear how to test these things, but that doesn't mean it's not important, right? So this is going to be sort of 3 lessons learned about cases that I ran into where models were not really doing what it seemed like they should be doing for sort of like subtle reasons. Yeah. Okay, so the first one is sort of classic deep learning. Again, we have inputs X and outputs Y. And in this project, though, the inputs and outputs were actually from a physics-based model. So I should have cited this picture over here. This is from a group at Virginia Tech studying soft tissue deformation. And one thing we were interested in was whether we could build a, like computing this deformation using their physics-based model was really computationally expensive. And so what we were interested in seeing is if we could train a data-driven model that would be a sort of a reduced order approximation to this. And in particular, they had a sort of like more mathy way of doing it that would build a reduced order model. And we were kind of interested in like, well, could a neural network do just as good? How does the performance of their reduced order model compare to machine learning model? So we used a fully connected deep neural network. We tried a whole bunch of hyperparameters, as is our way. We did this in TensorFlow. And so, yeah, so we wanted to compare with the physics-based reduced order model. Okay, and these are the results from an early draft of the paper. These are the physics-based reduced order models. So these are not their full physics model, but it's sort of a smart way of reducing and computational time and error. And these are a variety of machine learning based things. So the conclusion here was really that machine learning is not competing with their physics-based reduced order model in either computational cost or accuracy, right? So, this is not very competitive.
This error is comparing with the full order physics engine?
Yeah. So 0 would be the full order physics engine. That's right. However, so we got to wondering, so here we do have maybe on this axis, maybe we do have theory to guide us, right? Because we can write down how computationally intensive these models should be. And it was like, well, why is a machine learning model with like, I think it had like 2 layers or something. And this is, by the way, the student mislabeled this. This should be layer size rather than number of layers. I did not go back and regenerate a bunch of plots with dead data from this talk. So I just sort of took what we had as we were going along. So this is a not computationally expensive model at all. A layer size of 10 is like a really tiny matrix multiplication. So why is this so much more computationally expensive, right? So I got to wondering about that. And I'll tell you what the answer was after some digging. I mentioned we were using TensorFlow. TensorFlow has 2 types of execution. The default changed between TensorFlow 1 and TensorFlow 2, partly due to competition from PyTorch. So the default is called eager execution, and you evaluate each step immediately. So it's like you enter a Python command, it evaluates. You enter a Python command, it evaluates. But there's another way of running the computation on the back end, which is called graph execution, where it builds a computational graph, which is quite a bit faster. And here's just a comment from Towards Data Science that I found. That TensorFlow sets the eager execution as the default option. It does not bother you unless you are looking for trouble. So
easier, does that mean easier to implement or easier to execute? In what sense is it easier?
That's a good question. I mean, it's easier, I guess, in that it's the default. I think it's easier to use because you're getting your answers step by step. Yeah, apologies. Okay, but it's actually not hard once you know how to do it to switch. So this is what eager execution looks like. If you want to make a prediction on an input X, you just run model.predict and you get your output. To do graph execution, you can just wrap your model in a function, this TF function, and then now you have something that you can use to do your prediction. And the result is that the prediction time goes down by an order of magnitude or 2. Okay, so it was as simple as that, just sort of this obscure TensorFlow setting, and this result turned into that result, right? And so, what we found with that small tweak, we need 1 line of code change or something, is that the machine learning model is actually competitive for small model sizes, although we weren't able to get the error reduction that they were getting with their smarter model. Okay, so this is an obscure setting, relatively obscure. Maybe people who use TensorFlow all the time know these things, but that could have meaningfully affected our project conclusions. Okay, so we need to be careful before we drew any conclusions from that. Okay, so that's example one. I'm going to briefly talk about example two before I go to my favorite, which is example three. So example two, we're doing reinforcement learning. In reinforcement learning, you sort of specify a reward function, and you have agents that are sort of making decisions on the fly based on what they're seeing, and then they try to pick a decision that optimizes their reward function. Okay, so like I said before, game playing, autonomous vehicles, that type of thing, right? This is how they teach AlphaGo to play Go, or there's like a Gran Turismo driver that'll like beat the best Gran Turismo drivers in the world. Our case was multi-agent RL, so we had multiple agents that were trying to sort of achieve an objective together. We were using RL-lib, which was the package I mentioned earlier. Yeah, so we trained the model, and the rewards seemed to be improving nicely. They seemed like they should be doing what we wanted, and then we went to replay, and the agents did not do at all what we wanted. We were like, what the heck? So we thought maybe like the fact that our reward was going up was like, maybe we just defined a bad reward, right? And it wasn't actually the reward we wanted. So thought we made a mistake there. We thought we made a mistake in how we were implementing some things. So did we make a mistake in how we're visualizing? Maybe we're just drawing the wrong picture of the agents doing the right thing. We spent a bunch of time on all of these things. And then it turned out that then we started like digging, like, is it this or this? Okay, now we know it's this, is it this or this? And what we ended up finding is that the agent actions were supposed to be restricted to between -1 and 1. And actually they choose two actions in 2 dimensions. So each action should be between -1 and 1. But when we did the replay, 2 of the agents were doing the right thing, right? These are valid choices. And then 2 of the agents were doing something wildly, I don't even know what this is, right? So we were like, what the heck? That should be impossible. Well, then one of our students was looking around and was like, oh, it turns out this was a bug that was recently reported. And RL-lib is like a very popular package, but nevertheless, these things happen, right? Like, so again, it's worth digging. If you see, like, interrogate the model, see if it's doing what you want, and if not, dig and try to figure out why, right? So it turned out that in the replay, we were calling the agent action in a specific way, and if we called it in a slightly different way, then this type of behavior went away, and the agents didn't want it. So, it's just, like in a future version of RL-lib, this will be fixed and it won't be an issue. But, okay. Example 3. So here we are trying to train a classifier. So classification is a common machine learning application. Like if you, in the MNIST data set, you try to figure out what numbers are on these handwritten images. And so in our case, we're just going to classify into one of 2 groups. We've got a series of images, and we're going to do that. Our model is a deep neural network with a convolutional batch normalization. Remember that one, batch normalization, max pool, and linear layers. And this is all implemented in PyTorch. Okay, so we went to train this thing. The training, like, this is the loss function. So it's going down. That like looks good. It's doing what we want it to do. The loss is improving, but the validation did not seem to be improving. So, that's kind of weird. Are we just totally fitting, totally overfitting from the beginning? Maybe the problem's too hard, or, we need to try a bunch of different hyperparameters. I don't know what, right? So anyway, start digging, and alarm bells go off when we go to rerun. the prediction, and this is what the predictions look like. The truth is on the x-axis and the predictions are on the y-axis. And even when we rerun on the training data set to do the predictions, the results do not predict very well, right? Despite the fact that the training loss seem to be going down, okay? And yeah, so when we run on the training data, the data we just trained on, that was converging nicely, you know, we only get 59% right, and then we run on the validation, we get 62% right. So it's like we've learned nothing. So why? Okay, so again, I'll tell you the answer. PyTorch has two model modes. When you're training, you set it in training mode, which is used for, it does a bunch of extra stuff. It doesn't just do an evaluation, it computes gradients, it does a bunch of things, right, that you need for training. But when you go to do evaluation, when you just want to do a prediction, you don't care about all that stuff. And so you don't want to pay the cost of computing gradients that you don't need. And so you only compute the outputs, you set it in evaluation mode, okay? So we use train in evaluation mode and eval during validation and post-training predictions, which is exactly the way you're supposed to do it, okay? That's the right thing to do. However, I mentioned that we had a batch normalization layer, which is one of two layers that behaves entirely differently in the two modes, okay? And in particular, there's a setting called track running stats that when it's set to the default, the batch normalization layer forgets this training data statistics entirely, okay? So it totally forgets everything. And then, so the default in PyTorch is to tell this layer to forget everything it learned during training, okay? And I think the reason is because you don't necessarily want to assume that the statistics of the data you're going to be running on are the same as what you trained on. It seems weird to me to not sort of assume, to like maybe not make that the default, but whatever. Once we started knowing to look for this, you will find like hundreds of hits of people like, what the heck? Why is my classifier not doing what we wanted to do, right? So this is so weird. I sort of demonstrated this by just like, well, if I run eval over and over and over again on the same image, eventually the answer will converge to what we got when we just ran it in training mode with the statistics set, right? So super bizarre. Anyway, we turn track running stats to false. Now everything converges nicely, including the validation. When we go to do predictions, here, I guess we got 1 out of the 24 incorrect. Our training, we got 200 out of 200 correct, right? So like suddenly we have a very good classifier. We actually had a very good classifier from the beginning. We just had a flag that was set to false, okay? So again, a different obscure setting and a very popular machine learning was basically breaking our model, okay? And it would have been very easy to just sort of miss this, right? Like the normal thing to do would have been to like go try all these fancy image processing things to try to make our classifier better. And it turned out to just be this flag, okay? How am I on time?
You have about 5 minutes.
Oh, okay, great. I saw 151. Maybe okay, so I said I had 3 examples. I sort of half lied. I have 4 examples, but the 4th example is the same as the first example. Okay. So remember in this example, we fixed the TensorFlow execution and drove the computational cost down to sort of match the physics reduced ROM, right? Okay, I didn't explain that gap, right? Why are we getting such bad performance? And the answer is that we actually think that's right. That's why this is kind of annoying, right? Like in all of these, we didn't know if anything was going wrong. We just sort of intuited that maybe something was going wrong, right? This still feels like it should be, like maybe we should be able to close this, but man, we beat the heck out of this. We tried every hyperparameter set we could think of. We made huge models and it never really, we sort of got this like Pareto front where they just like never seemed to do better. Now this map is like really weird. It's like from a very low dimensional parameter space to like a very high dimensional finite element output. So it might be something, you know, related to that. You know, by the way, typically you would say like, well, why should I be able to predict a high dimensional output from a low dimensional input? But we know it exists because there's a physics model that does it, right? So there is a map that exists. It's just, you know, maybe we're just having a really hard time approximating it because it's this weird dimensional LP. Okay. So yeah, so anyway, this is just a fourth example to just sort of say these issues are tricky because we don't always know, like we don't have theory to tell us how close we should be getting, right? All we can do is just try. Did you have a question?
I just comment. I mean, I think sometimes it highlights that often machine learning is not the answer.
Yeah.
Right? Why you? I mean, it's not that you're a perfect good model. We don't need to have machine learning to do
Yeah.
something.
I have a mathematics friend that does a bunch of ROMs, and he was very happy with this. Yeah, he freaking loved it. And he loved all the pain we had in trying to get it. Okay, so, yeah, okay, so, you know, just conclusions, right? These models are super powerful, obviously, right? Like we've all been wowed by like ChatGPT and all these things, right? But they are pretty opaque. And if something's wrong, if anything, it isn't always clear. So, and you know, just to, maybe I should have said this from the beginning, right? There can be a lot of pressure to just trust them, right? If you have a deadline, deliverable, you know, on the academic side, if you like, you have a publication deadline, right? Like there can be a lot of pressure to just like, yeah, this seems right, right? But it's really worth trying to dig, if there's anything that's counterintuitive, it's really worth digging into them to try to make sense of it and sort of see what's driving the decision, because it may not be what you think it is. Okay.
Time for one question. No one else has a question? I have a question.
Sure.
So when did you compare on the very first problem? Did you compare the TensorFlow process to, and obviously you did lots of work, but to a similar approach using PyTorch? Like, do you feel like PyTorch is hiding fewer things than it sounds like TensorFlow is trying to hide?
PyTorch is a little bit more a little bit more, you can tune more things in PyTorch, but I sort of suspect that, so we did not try.
Okay.
But I sort of suspect that we would see similar results, unless we tried something, you know, different. I sort of trust that their training and that kind of thing is mostly the same, plus or minus a few of these small, you know.
Thank you so much.